Moving onward to example 6, let's find the Laplace transform for t to the power n, where n is a positive integer. So by our definition of the Laplace transform, this is an integral from 0 to infinity of our function t to the n times e to the minus st dt. Again, this is an improper integral, so let's write out the limit. Limit as b goes to infinity. Integral from 0 to b of t to the n e to the minus st dt. Now we'll do integration by parts here with u equal to t to the n. Du is n t to the n minus 1 dt. The dv will be the exponential. dv is e to the minus st. v is, again, we have e to a constant times t dt. Antiderivative is 1 over the constant, negative 1 over s, e to the minus st. We integrate by parts. We'll have limit as b goes to infinity. U times v gives me negative 1 over s, t to the n, e to the minus st, evaluated from 0 to b, minus the integral of v du. So minus a minus, which will give me a plus. For the constants, we'll have n over s. Let's just put those outside of the new integral. Integral from 0 to b of t to the n minus 1 e to the minus st dt. Now when we plug in 0 and b, we'll have a limit as b goes to infinity. We'll have a negative 1 over s b to the n e to the minus sb minus, we plug in 0, we're just going to get 0. Okay. Now I'm going to go ahead and just rewrite this as n over s, integral from 0 to infinity. Let's throw that limit back in. T to the n minus 1, e to the minus st dt. Okay, looking at this limit, it's actually indeterminate. The b to the n will go to infinity. The e to the negative s times b will go to 0 as long as s is positive. But the exponential goes to 0 faster than any power b to the n. You can repeat L'Hopital's rule over and over n times. Eventually the b to the n will go away, but you'll still have that exponential function. And so this limit will be 0. So this whole piece goes away, and we're just left with n over s times this. But notice that this is simply the Laplace transform of t to the n minus 1. So we've got that this is n over s times Laplace transform of t to the n minus 1. Now, we could repeat that process over and over, but let's just look at what this implies for some values of n. Now, first of all, for n equal to 1, we've already seen that the Laplace transform of t to the first is equal to 1 over s squared. We got that in example 2. Now, we can use recursion to find Laplace transforms for higher powers, like with n equal to 2, Laplace transform of t squared. Using this property, n equal to 2, we're going to have 2 over s times the Laplace transform of t to the n minus 1. With n equal to 2, that means Laplace transform of t to the first. but that's just 2 over s times our Laplace transform of t to the first was 1 over s squared. So we now have 2 over s cubed for the Laplace transform of t squared, n equal to 3. Laplace transform of t to the n, Laplace transform of t cubed will be, again, use this property, n over s, that's 3 over s. Laplace transform of t to the n minus 1, that's the Laplace transform of t squared. So we have 3 over s times, we already know the Laplace transform of t squared is 2 over s cubed. So now we have 3 times 2 over s to the fourth. Moving on to n equal to 4. Laplace transform of t to the fourth is n over s. That's 4 over s. Laplace transform of t to the n minus 1. n is 4, so now we have t cubed. That's 4 over s times, we just saw that the Laplace transform of t cubed was 3 times 2 over s to the fourth. So we have that the Laplace transform of t to the fourth is 4 times 3 times 2 over s to the fifth. Now notice we've got a pattern emerging. We look at a Laplace transform of t to the n. The numerator is 1 here, 2 here, 3 times 2, 4 times 3 times 2. The numerator is n factorial. And the denominator is simply s to the n plus 1 power. Power down here is always 1 more than the original n. And that's going to work for all positive integers n. Now, in fact, this also works for n equal to 0. We saw previously in example 2 that the Laplace transform of a constant, like the Laplace transform of 1, was 1 over s. And if we think of 1 as being t to the 0 power, Laplace transform of t to the 0 would be 0 factorial, which is 1, divided by s to the 0 plus 1, 1 over s. So in fact, this even works for n equal to 0, 1, 2, 3, any non-negative integer.